That's me, without the beard. I'm going to tell you a bit about the concept we call biointegrated carbon capture and utilization today, which is a concept we've been working for some years on, and also as part of Cork. And it's basically trying to capture CO2 from industrial sources like flue gas, so dilute sources, and then transforming them into e-methane or synthetic natural gas that can substitute our use of fossil fuels. And I boldly said, when chemistry and biology meets, because it's an unholy or holy alliance of biology and chemistry meeting here, trying to rethink how we do carbon capture. And maybe just now I got what Lasse wanted to accelerate things from the lab and just to give you the journey here when we started working on this and trying to think, okay, maybe we can rethink how we do carbon capture. Maybe we can rethink how we combine chemistry. And traditionally, carbon capture is a purely chemical process. But we thought maybe add a pinch of microbes and then get the benefits from there. But for getting from the initial state, and we killed a lot of microbes these 3 years, I can say, we're getting from there, and then also then going from batch scale and then to continuous scale in lab still. We have now, over the last couple of years, spent some time and some effort getting into outside lab. It's still within the Aarhus campus in that way, so we are still a bit in lab. But on industrial flue gases that are realistic and can be comparable to what we see out in industry. I'll take you through this, but first, maybe just a bit of background. And I think, the need for renewable fuels, that is quite clear to everyone. And I think natural gas has really been top of mind on many people the last couple of years, because we realized how dependent Europe was on external gas supply. So 80%, 85% of the gas we get into Europe is imported from other countries. So we are extremely dependent on this. And what we use is around 333 billion normal cubic meters of methane a year. That is a lot. And there's no elasticity. If we miss it, we are missing it dearly. Right now, it's mainly used for power and energy. And maybe that's not a super good way of using this, but in the future, utility, so hard-to-abate sectors, marine sectors, especially, will be more and more prone to use this instead of heavy bunker fuel. And there are some political regulations going on EU level that will simply support that implementation as well. Back to our process. What we do is maybe a classical Power-to-X chain, or maybe not that classical, because you have your wind turbines here, your solar panels, you have your electrolysis, so you use that to split water, and you get the hydrogen, and then you react the hydrogen with CO2. And what we do is to take microbes as a catalyst. So Troels uses a chemical catalyst. We use microbes. And we have, for many years, worked with biogas as a source of CO2. Because if you want to go to natural gas, well, then you're almost halfway there, because biogas is half methane and half CO2. But we have also, over the years now, as you could see, worked with flue gas, trying to take that. But unfortunately, flue gas is extremely diluted. It's only 5% or 10% of CO2, depending on the fuel and the combustion methods. So that also means that you have to do something different if you want to produce methane that can then be produced for these things. And if you really want to tackle climate challenge and use CO2 as a feedstock on large scale, well, flue gases are the right ones to tackle, because they are the most dominant ones. We just made a table here showing the composition, so we can see it between these around these 10%, a bit higher for cement and steel production, but otherwise for the power sector, quite low. But the tons, they're on gigaton scale. Whereas if you go for biogas, well, you are not really on gigaton scale. So you can get far with biogas, and you should use all the biogas that you want on this, but it will not get you to where you want to. If you want to substitute the natural gas consumption that we have today, well, we have to tackle flue gases. And I think, Andrea, you said this morning, envision your success. Our success is we can substitute a significant fraction of the natural gas that we do today. That's really the goal for this. We know that it's not an either or, it's in both and, so other technologies will come into place. But we will tackle this. That's the goal. Unfortunately, if you want to tackle flue gas, it's also, you need to capture it first. And capture is, no matter how you use it, it's extremely energy intensive. So here it's a classical chain of capture. So you have your absorption here of your CO2, And then you desoap the process, and down here you can see the gigajoules you use for that. And then you compress it, and then you can use it for something. Now we put in biomethanation because that's what we do, but it could also be a chemical methanation process. But that means that there's a lot of energy involved in this, and especially the desorption step is intensive. So around 90% of all the energy used in carbon capture, that's actually used for that desorption step. So if you really want to employ this carbon capture on larger scale, we need to tackle this in some way. So we came up with an idea and said, why not? I mean, microbes, they want to use CO2 when it's in a dissolved form. Why not try to use biotechnology for exactly that thing? And it might sound a bit crazy. It was a bit crazy, but we basically jumped that part with the desorption, and then went directly from absorption, and then throwing in the CO2-loaded carbon capture agents into our bioreactors, and realized that the microbes, well, most of the time they died, but we actually found some blends and some operational conditions where you could hit that spot where you could let the microbes take out the CO2 and then transform it to methane, and then recycling the liquid back to the absorption tower. So we could actually skip all that and reducing your energy by 3.6 gigajoules per ton of CO2. That's a substantial fraction. Of course, you still need to add the electrolysis hydrogen. That's still expensive, but you can really reduce the cost of CO2 capture quite significantly. So that was really the effort, but also we realized that it was not an easy fix. You can not just mix it and then it works. And that went into to try to formulate, okay, what are the developments that we need here? And we read the developments on 3 pillars. We need enhanced microbiology. So that was also still keeping to the fundamental research, trying to understand what happens when you mix carbon capture on microbes. And I think, Jeff, you said don't let go of fundamental research. That's still important. That's still at the core of what we do, understanding this. And out here, if you know your microbes, these are happy microbes. They are unhappy microbes when you mix it with capture agents. For sure, there's something that we can learn on this. Choosing the right microbes, that was absolutely key to our success. And then also choosing the right capture agents. And we teamed up with Kim Dosbjerg from the team for chemistry, AU Chemistry, and have now screened around 100 capture agents of different parts, trying to find what is compatible with our biology, and can we begin to synthesize new capture technology as well. And it actually seems to be quite promising at this. And then I would show some results from the last part, because we also realized we needed some new bioreactor designs. We were working in 100 milliliter scale in the laboratory, so we needed to go up in scale in some kind of way. And that had fueled a lot of you can say, both the science and engineering. And what we did was to try to develop the reactors we had from lab scale. So that's a half a liter to it's a liter reactor with spinning around and getting some conversion of the captured CO2. But we made a new development. I'm switching here. Up to these reactors here that are standing outside in our capture lab now. 10-liter reactors that are coupled directly to a flue gas emitter here. And we could actually, by these developments, accelerate our conversion from to 8 liters per liter per day. And in transferable, that's what we can do for biogas now. So we're actually on par with what we can do on biogas. So a couple of years of testing a new reactor design, 600,000 liters of raw flue gas running through this and actually being treated and converted to natural gas quality methane. That really made the efforts here. So 16 times we were able to accelerate the conversion rates. And also made a new platform for us testing all the capture agents that we developed. So all the new things coming out of the lab at this size, we could actually put it in and test it under real-time conditions. And right now we have now a full process chain. So this is the biogas coming into our engine. It's burned. It's 600 kilowatt engine. Flue gas coming out of the stack. We scrub it in the absorption unit, and then we use our reactors here to convert it to gas grid quality, and then return back the absorption unit, liquid. Pictures here. And then we can return or complete the process. So that's really the scaffold, the part that we are building on right now. And we were lucky to get an accelerator grant for accelerating this kind of technology. So we had also had the money to build up new lab scale facilities, build up the reactor capacity that we needed. Last part of this is then, okay, so then what? And I would say we know that this BICCU process, we're able to reduce both CAPEX and OPEX. We reduce the energy content or the energy use, but we also reduce the amount of units that we need for this. But we also know that there's a lot of new research that we need for this. I mean, we need to increase the performance even more, increase the robustness of this, and make new research and new inventions for sure. But also scaling in parallel is part of that journey, because we need to scale to be able to quantify cost much more reliably than we can do today. We need to integrate with other technologies, both to make the challenges, but also the benefits of integration. And then we need to get industrial emitters on board. And we have been out talking with a lot of people. This is my local power plant, 200 megawatts in my backyard, not completely, but going down there and seeing what happens out there. And I think that humbles you a bit. You think that this can be done, but get outside your lab, reach the reality, standing looking up at a 20-meter high chimney. You get a sense of perspective in some way of what you're doing in the lab. So that's been a good journey. And then I would say, I mean, there's a lot of challenges for sure, and PTX has really been challenged over the last couple of years here. The climate agenda, I still put it on as a driver. There's still a drive to do something about the climate. But I would also say, of course, there's a bit of resistance in different places. But again, energy and security, that's high on the agenda. And this is tapping directly into this. Then there's this new EU directive, RED III, taps into that we should be able to make renewable fuels of non-biological origin, RFNBO fuels, which really forces implementation to, for example, the marine industry. They have to do something about that. So we need to produce this. Of course, renewable power is absolute must if you want to do something with PTX. And then on the positive side, we produce a fuel that is directly implementable to the gas grid in Europe. So we can send gas from the northern tip of Denmark to Naples if we want to do that. So in that way, infrastructure at least is in place. Yeah. 12 minutes, yes. But yeah, thank you.